So training a multi-layer perceptron or multi-layered neural network. So we have many layers here, that's why this is called a multi-layer neural network. So we have input layer, we have a layer 1, layer 2, and this is output layer. So this is how a multi-layer perceptron looks with two layers. We may have more than two layers or multiple layers. So let us now understand the notations which we already discussed. So we have data set here in the form of xi's and yi. That means we will have x1 comma y1, where x1 is the input, y1 is the output or class label for this input. x2 comma y2, x2 is the input and y2 is the class label or class of this input. So likewise we will have a data set of size xn comma yn, right? So now here this x is input, but that input may have many features or it may be a multi-dimensional input. So that's why I can write this as x1 as x11, x12, x13, so on and so forth, x1n. So this x input or x1 input has, let's say, n features or n dimensions. So that's why I am writing this as x11 means first feature of input 1, x12 means second feature of input 1, x13 means third feature of input 1, likewise x1n means nth feature of input 1. So that's why it makes sense to write this or let's say if I have this xi, if this is xi, this becomes xi1, xi2, xi3 and xin. So that is how I can represent this input xi which has n dimensions, right? So that's what we are doing here. We are giving this x as input here, xi as input with 4 dimensions or 4 features. Here every input has 4 features. That's what we are considering here. Okay, so now let's talk about weights. So this weight representation is wi or wkij. That means this weight is going in kth layer from ith neuron in the previous layer to the jth neuron in the next layer. For example, if I talk about this W211 means this weight W2 is going to layer number 2 from first neuron in the previous layer, that is this layer, to the first neuron in the next layer, that is this layer, right? Okay, so now similarly here this W111 means this is the weight going in layer 1 from first input or first feature here to the first neuron here, right? So now let's talk about these functions or activation functions which are there in these neurons. So F11 or if I write Fij says that this function, activation function, is in the neuron in the ith layer neuron and the jth neuron from the top. That means this neuron is in the ith layer and its number is j from top. For example, if I say F11 means this neuron is in the first layer and it is the first neuron from top, right? So numbering is like this is layer number and this j says what is its number from top, what is the neuron number from top, right? Okay, now this O11 says or Oj says this is the output. O says output of neuron in ith layer and its number is j from top. So this Oj is similar, or this output number will be similar to this function, activation function here. Okay, so now this is y hat says this is the predicted output for this input. If I was giving xi as input, for that xi the class label or output was yi, but the predicted output, that means the output generated by our neural network, is yi hat. We are calling it as yi hat. And this L says what is the loss, that means how different is this predicted output from the actual output, how different is this predicted output from the actual output, that is called as loss. Okay, with these notations, let us start how to train this multi-layer perceptron. So training a multi-layer perceptron means, or training a single neuron model means finding the weights, finding these weights, finding, for simplicity I have written only one weight here. I will have 4 into 3, 12 weights here, right? So here it will be W1 W1 1 2. This weight will be W1 1 2. That means this W1 1 2, that means this weight is going in layer 1 and it is coming from this first feature and going to the second neuron here, right? Similarly here, if I write this weight will be W2 because it is going in layer 2 and it is coming from neuron 3. It is coming from, this is neuron 3 and it is going into neuron 2. So W3 W2 3 2. So training a multi-layer perceptron means finding all of these weights, so that we can have as less loss as possible. That means we want these predicted output to be very close or exactly equal to the actual output. Okay, so now how to train, right? So we will use what is called as gradient descent or stochastic gradient descent, SGD, right? Now what do we do in this SGD? We first initialize the weights randomly. So these weights will be initialized randomly. That is the first step. Next, after initializing the weight, define the loss function. So the loss function here is loss is equal to, if I write loss for a single input, I will call it as Li is equal to Yi minus Yi hat square. It is a squared loss we are considering for this discussion, plus some regularizer, right? So this regularizer will be used, this regularizer will be on the weights, right? So this is the loss for this single input. Now loss for all the inputs, it's sum of the individual losses. This is the individual loss, right? So loss of all the inputs will be, or let me call this loss as L is equal to sum over I is equal to 1 to n. If there are n inputs, this will be sum from 1 to n, yi minus yi hat whole square plus regularizer. So this is the total loss. Now what we want to optimize this loss. Means we want to reduce this loss, reducing the loss. So how to reduce this loss? For reducing this loss, you see this loss is in this loss we have y and y hat, right? Now in the data set we have data in the format xi comma yi. So if we look at this neural network, we have x's and x input, we are giving x's as input and we are getting y as output, right? And we have this w. There are so what is unknown here? Unknown is only w's, I mean, or the variables. The variables are only w's. So we cannot change the input and the output. We cannot change this x's and y's, but we can change this weights so that we can have this minimized loss, right? So that's what we want to do. We want to minimize this loss, right? So how to minimize this loss? By using SGD. So SGD says initialize the weights randomly, right? After initializing the weights randomly and defining the loss function, the third step is calculate a new w new is equal to w old minus eta times derivative of loss with respect to derivative of w old, right? By using this formula we will compute the new W's, new weights, right? Now, till what time we will compute this new W's? Till the time of convergence. Convergence means the new weights are very close to old weights. That means there is very less updation in the weights, right? Till that time we will update the weights, right? Now, the important point here is how will I compute this, right? The crucial or crux here is to compute these derivatives of loss with respect to old. So we have to compute, derivative of loss with respect to W1, or if I go here, if I show, we have to update each of these weights. We have to update all of these weights. So here we have 12 weights, here we have 9 weights, and here we have 2 weights. So we have to update all of these weights. That means if I want to update this W3, this weight, so I'll have to say W3 11 new is equal to W3 11 old minus eta times derivative of loss with respect to W3 with respect to W3 11 old, right? So that derivative we have to compute, right? Similarly, if I want to update this weight, I will have to compute use the same formula, and that time I'll have to compute the derivative of loss with respect to this weight. So I'll need to compute the derivatives of loss with respect to all weights, because I'll have to update all weights. So now, as I said, the crux or important thing is how to compute this derivative. This is eta is called as learning rate. We'll learn or discuss later how to compute or how to have this learning rate. Right? So the crux of the discussion here is to compute these derivatives. So let's see here how to compute these derivatives graphically. So I want to compute these derivatives. Let me have some space here. Okay. So let us first compute the derivatives in this layer, right? So first let us compute a derivative of this W311. So derivative of loss with respect to derivative of with respect to W311, right? So I want to compute this derivative of loss with respect to this. That means I want to update this weight. That's why I'm computing this derivative, right? So is equal to, right, is equal to, so derivative of loss with respect to this, I want to compute this. I want to compute, let me use this color here. I want to compute this derivative, right? So I will use the chain rule, which is the crux of calculating all these derivatives, right? So I'll compute derivative. In order to compute this derivative, I'll compute this derivative, right, and then this derivative. So derivative of loss with respect to W3 is equal to derivative of loss with respect to O31, derivative of O31, right, and then this derivative of this O31 with respect to W311 into derivative of O31 with respect to derivative of W311, right? So this is called a chain rule, right? So we have this term has to be same as this term, right? And then this is equal to dou L. It is called as dou L by dou W311, right? That is how I can compute the derivative of loss with respect to W311. Similarly, I can compute the derivative of this, right? So let me do it quickly. So derivative of loss with respect to W321 is equal to derivative of loss with respect to O31 now, with respect to O31, and then this derivative of O31 with respect to this weight, derivative of O31 with respect to derivative of W321. So that is how I can compute the derivatives in this layer. Now let us see how to compute the derivatives in the second in this layer, right? So let me again have some space here. Okay, so I want to compute derivative of loss with respect to W211. Now I want to compute this derivative. Now derivative of loss is derivative of loss with respect to this, derivative of loss with respect to W211. I want to update this weight. That's why I want to update this weight. That's why I want to compute this derivative is equal to, in order to compute this derivative, I will compute derivative of loss with respect to O31, right? And O31 is computed with respect to O21, right? And O21 then will be computed with respect to W211. So right, this path I will be following this and this, right? So is equal to derivative of loss with respect to O31, right? Because this O31 is being transmitted here, right? So derivative of loss with respect to O31, and then this derivative of O31 with respect to O21 into derivative of O31 with respect to derivative of O21, and then finally this O21 with respect to W211, derivative of O21 with respect to derivative of W211. So that is how I can compute this derivative. So again, it's a chain rule. So this is the same as this is same as this, and finally we have this term here and here, right? So similarly, all other weights can be updated by computing their respective derivatives, right? Now let us see how to compute the derivatives in this layer, right? Okay, so let me again have some space here. So this case, before computing these derivatives, let us discuss a case where I have, let's say, this x is going in this function f of x, and this x is again going in this function h of x or g of x, let me say, and then these are coming here in h of x, and then this h of x is going into k of x, let's say k of x, right? So if I discuss about this case, how to compute derivative of this k with respect to this x. So I want to compute dk by dx, right? Dk by dx, or let me take it as y. I want to have this as y. So what I want to compute is dy or dou y by dou x. So that is equal to, right? So this h output is going in y, so I can write this as dy by dh, right? Let me not write this x, right? So dy by dh and dh by dx. Derivative of what I am doing is this with respect to this, and then this with respect to this. Let me not worry about this for now. So this will be dh by dx, right? So dy by dh and dh by dx. Now how to compute this dh by dx? You see this dh by dx, so we have two paths which are coming to this. This is the first path coming from x to h, and this is the second path coming here, and both are parallel paths, right? So when we have parallel paths, I take the derivative of this path plus the derivative of this path. So that means this dh by dx, if I write dh by dx is equal to this, with respect to this, is equal to dh by df into df by dx, this path, plus dh by dg into dg by dx. So I will be writing here. So this is equal to this path derivative plus this path derivative, right? So dh by df or dou h by dou f, because they are partial derivative, dou h by dou f into dou f by dou x, plus this path derivative, dou h by dou g into dou g by dou x. So that is how I compute derivative of this with respect to this. We have these two parallel paths, so I have to take derivative of this path plus derivative of this path. Again, chain rule will be applied here and here as well. So that is how I will get this derivative, and now I'll substitute this here. So then I'll get the derivative of this dy by dx. So the same structure we have here. This we have this. I want to compute this, right? This derivative. So we have this path, right? And this is one more path which are coming here, and then we have this output going into L. So this H is similar to O31, this Y is similar to this loss, right? And then we have this path which is similar to this path, and this path is similar to this path, and this is X here, right? Okay, so let's use this knowledge to compute the derivative of this W111. So W1, let me see whether I'll be able to write here or not. Dou L by dou W111. That's what I want to compute. Derivative of loss with respect to this is equal to derivative of loss with respect to O31. It is like derivative of Y with respect to H, right? So derivative of loss with respect to dou O31 into derivative of O31 with respect to this W111. So derivative of O31 with respect to W111, right? Now I have to compute this. So let me now make some space here. Just a moment. Okay, so now how to compute this derivative of this with respect to this. As I said, we have two paths, this path plus this path. So I have to compute derivative of O31 with respect to W111. So W111. So this derivative of O31 with respect to W111 is equal to derivative of this path plus derivative of this path derivative plus this path derivative. Again, I will be employing the chain rule here. So derivative of O31 with respect to this O21, right? On this path I have this O21, right? So O31 with respect to O21, and then O21 with respect to O11. Derivative of O21 with respect to O11. This is O11 here, O11, right? So derivative of this O21 with respect to this, and then this finally derivative of this with respect to this into derivative of O11 with respect to derivative of W111, right? So this is the derivative of this path, right? Now let me take the derivative of this path and add it with this path. So derivative of this path, that is derivative of O31 with respect to O22, derivative of O31 with respect to derivative of O22 into derivative of O22 with respect to O11, O22 with respect to O11, this with respect to this, and finally this with respect to this, derivative of O11 with respect to W111, right? So now if I substitute this term in here in the bracket, I'll get the derivative of this loss with respect to W111. And once I have this, by using the formula, which formula? This formula, right? This formula, right? I have this term calculated, right? I have calculated all the derivatives, then I can update all the weights. So that is how we can train a multi-layer perceptron. The point here is we need to compute all of these weights, right? So that's it for this video.